Today, we get to hear from Tyler Knudsen. He got his master's degree in geology from University of Nevada, Las Vegas. Since then, Tyler has spent his career with the Utah Department of Natural Resources, studying geology and mapping southern Utah in Cedar City and Parowan valleys, Zion National Park, the St. George Basin, and the Glen Canyon National Recreation Area. Today, he's taking us on a hike of Thunderbird Gardens. And in order to speed up the hiking from one geological area to the next, he actually videotaped it in advance and sped up the walking. So we get to watch the video, and then we're going to do some questions and answers afterwards. Thank you for joining us.
Hi everybody, we're here at Thunderbird Gardens, just east of Cedar City, and today we'll be talking about the wonderful geology that is exposed in this area and is very accessible to Cedar City residents. So if you're not familiar with the Thunderbird Gardens area, we are just east of the golf course. And so to get here, if you're going down Main Street in Cedar City, you want to turn east, and I believe there is a sign there on Main Street on a road that goes to the golf course. And just stay on that road. Eventually that paved road turns to dirt, and you just keep traveling east basically until it ends at the Thunderbird Garden trailhead. So it's a really easily accessible. And on your way to the trailhead, you will go by these flood retention basins, and that's where we're going to start out. Today's guide is talking a little bit about the geology that you can see near these retention basins, which is also where the Razorback Trail begins, which is right behind us here. So this area records about 150 million years worth of geology in the rocks and the various structures that you can see here. A really protracted, interesting history, not only that produced the different rocks that you see here, but that has also tilted these rocks up and has faulted these rocks into the amazing formations that we see at Thunderbird Gardens today. So from here, you can really see, I mean, the rocks are basically color-coded. You've got red rocks, you've got orange rocks, you've got gray rocks, and everything in between. And so at this hill that's across the valley, we're looking at mostly Jurassic age rocks. So these are about 200 million years old. Starting at the base of this hillside, we have what's called the Mojave Formation. And about mid-slope, where the rocks have a little bit of a purplish hue, that is the Springdale Sandstone. And then at the very skyline, that orange-colored rock, of course, is the infamous Navajo Sandstone that has made Zion National Park famous just to our south. So these rocks are mostly continental deposition. And so at this time, we were much closer to the equator, and to the west was the ocean. We were very close to the coast. So you can kind of think we didn't have the big mountain ranges that we have today. We were on kind of a flat coastal plain, and there were a number of river systems that went from highlands to the east towards the ocean that was to the west. And so these are sands and silts and mud that was deposited in these river systems and delta systems and swamps that were in these lowlands along this coast of Pangaea, which was a supercontinent that existed at the time. So that's that hill. Lower down on that slope, you get into Triassic. So the really colorful reddish colored rocks are your Jurassic section. Lower on the slope, this smaller hill where it's kind of gray and even a little bit purple, you get down into Triassic age rocks, which are a little bit older. You know, typically as you go down in section in the geologic section, you get into older and older rocks. And so you got the Triassic section there. And at skyline, peaking that, on the peak of that little knoll, are tan sandstones of the Shinneramp conglomerate, which is a sandstone that was deposited in braided streams near this coastal plain. And below that are purple mudstones that locally are known as the blue clay, and particularly down in St. George, those blue clays cause all types of problems. But here, luckily, they're well exposed up in the mountain range, but we don't find them in town, so we don't have a lot of problems with those clays as they are expansive. When they get wet, they soak in that water and they can expand, and it causes all kinds of issues for homes that may have been built on top of those clays. And so that's the Chinle Formation over there. Okay, so if we look behind us, we kind of have what is a typical, what we would call a strike valley, where that Shinnerump conglomerate, that kind of more durable sandstone, is capping both sides of this valley, and then the more easily eroded rocks in the middle, which are the Moenkopi Formation, which is mostly mudstones and shales, very easily erodible, that kind of erodes out over time, and those stronger sandstones hold up either side of that valley, creating that what we call strike valley. And so the Moenkopi Formation is another common formation that creates a lot of the beautiful badlands that we have in southwestern Utah. Beautifully exposed down near the St. George Basin. Has a little bit less exposure here, but is nonetheless very, very pretty to look at. And again, those rocks were deposited at the ocean margin, and kind of as sea level rose and as it fell, it kind of gave us all those multiple colored layers that you see within the Moenkopi. Sometimes you'll have white layers that are rich in gypsum, and others are just kind of red shales, and that just depends on whether sea level was high or whether sea level was low, would kind of control what type of and what color of rocks you would end up with. And so one interesting thing to point out is these rocks are basically the same. So we got Shinnerump conglomerate on this side, Shinnerump conglomerate on this side. They're both dipping and are inclined at about 45 degrees, and they are faulted. They are not continuous. So basically the whole rock sequence here has been repeated. And this was repeated along what we call a thrust fault. And so this is when great forces compress the Earth's crust, it buckles, and basically the Earth's crust faults up and then rides over the top of itself. And so that's why we have a repeated section here of a large part of the Moenkopi Formation and that Shinnerump conglomerate sandstone are both repeated here. And so that really is the story of why these rocks are no longer flat here. It was about 100 million years ago when we had the severe orogeny, which is basically a mountain building event that caused this compression and has folded these rocks, tilted them up at an angle, and in some places have created these thrust faults where rocks are repeated. So that's the basic story here. We'll go on up canyon and look at some more stuff now. Okay, here we're just north of the Thunderbird Gardens main trailhead and parking area. And there's a little dirt road that'll take you up into this little valley with all the orange red rock. And this is a really good place to talk about the Jurassic Age Navajo Sandstone. That is, of course, very much famous in a lot of southern Utah. And the Navajo Sandstone basically is the record of the largest paleo sand dune field in the Earth's history that we know of. So this thing this big sand pile was essentially extended from Colorado down to southern California, and at its deepest point, which is near Zion National Park, is a little over 2,000 feet thick. So this was an impressive sand dune field. It would have been much larger than today's Sahara Desert by quite a bit. And the reason, before when we were lower down in the section, we were talking about swamps and being near the coast and river systems. And by the time we get to the deposition of the Navajo Sandstone, an island arc develops out in the ocean off to the west, which creates a rain shadow and puts the area that was southwestern Utah into this rain shadow, which of course results in very little precipitation, being on the lee side of this large mountain range, and then this desert ensues. So we go from swamps to just a huge Sahara-like desert. And geologists have done studies on the provenance, or where all the sand came from. And we believe that it actually is sourced from the Proto-Appalachian Mountains, so clear on the other side of the continent. We believe there were large river systems that flowed from the Appalachian Mountains, which would have been much larger than they are today. And that river system carried sediment, including the sand that would eventually become the Navajo Sandstone, in that river system across the continent to here near Utah. And then the arid winds would whip up and pick up that sand out of the distal end of those river systems and pile them up into these great sand dunes. And so kind of typical of the Navajo Sandstone are the cross beds. Of course, here everything is kind of tilted as part of that fold that I talked about from the severe orogeny, that mountain building event. But normally you will find the beds dipping at an angle, which is basically the lee side of these sand dunes. You get the preservation as the prevailing wind blows the sand up and over the crest of the dune. What you get preserved is where it spills over the crest of that sand dune, and you get those layers at an angle, and that's how you get those cross beds. And if the wind direction changes, you get erosion, and you get cross beds that are oriented at a different direction. So a lot of times you'll get cross beds that are going one way, and then they'll go another way. And it's because of the winds are constantly shifting, you get a variety of different orientations of those cross beds. So I think that's all I wanted to point out here. We'll go up the canyon and look at a few more things. Okay, here we are about 100 yards up the Thors Hideout trail. And here it's kind of an old Jeep trail. It's pretty wide, but you don't want to miss as you're walking along, look at your feet, and when you see these kind of bluish gray rocks, you'll definitely want to take a minute and look at these. They look very much different than the surrounding orange Navajo sandstone, and that's because they've been washed out of the canyon quite some distance. And so they're worth looking at because these are Cretaceous in age. So once you get up above the Navajo Sandstone and you get up through the Carmel Formation and out of the Jurassic section, you get into the Cretaceous section, which is very well known for its fossils. And so in the Cretaceous time, and we won't look directly at those rocks, we'll look at some stuff that's kind of washed down, and we'll look at some landslide deposits. But at this time, again, we kind of return to marine deposition. So instead of continental rivers and lakes and that sort of thing, we're back to marine deposition near the beach and shallow marine. And so we get a lot of different types of marine life. And so here, this rock is, it's just all over the place, is just chock full of shale hash and little pelecypods, which are, similar to modern day clams and oysters. And so you'll want to kind of inspect through these. You can find all kinds of really neat fossils and very common. And so one thing that's different about these marine rocks versus the Moenkopi and some of the marine rocks we talked about earlier is during the Cretaceous time, the ocean was actually off to our east. So this was an ocean that occupied the interior of the continent rather than off to the west of what was Pangaea, or the North American continent, would eventually be the North American continent. So we'll keep venturing up the canyon, but don't forget to look at these. Okay, so now we're here near the junction of the bottom of the Ghost Flat Trail and Thors Hideout Trail. And if you look north from near this junction, you can see a really cool geologic relationship. And so here, of course, you've got on that lower slope that orange Navajo Sandstone, which is Jurassic in age. And then on top of that are rocks that are completely different looking. There's kind of some grayish purplish mudstone in there, and then just kind of random rotated boulders of kind of a grayish, yellowish gray sandstone, just kind of all jumbled together on top of the Navajo Sandstone. And so what you're looking at up on top there are those Cretaceous rocks. I kind of pointed out some of the fossiliferous nature that had washed down into the stream bed below. But here you've got a much thicker deposit, and you don't normally find Cretaceous rocks directly on top of the Navajo Sandstone. There's a whole geologic section missing there. And the fact that there is no bedding, that everything's just kind of jumbled together, really gives you a clue as to how these rocks got there. And how they got there is because basically we're looking at a big landslide. And so landslides are very common in the Cretaceous section because of those clay-rich units, which are very weak and are susceptible to failure, especially when they get wet. When we have wet years and groundwater levels get elevated, those rocks on slopes become very unstable and can start to slide. And so that's what's happened here. This landslide most likely occurred thousands of years ago. We can tell by how incised these drainages must have had quite a bit of time to cut down these canyons into the landslide deposit. So we know it happened a while ago. But this was a large landslide, and so it covers a couple of square miles here, and you won't find any bedding. Everything's just kind of chaotic over there. And even though the whole landslide complex, it may have occurred thousands of years ago, there are smaller sections where these modern streams have incised and cut these steep walled canyons. There are smaller landslides that occur as this very weak landslide material sloughs into these canyons. So there are many small, even in historic times, active landslides that are within this larger landslide complex. And so these are common along the Hurricane Cliffs east of Cedar City. And so luckily this is BLM land and will not be developed. But as geologists, that's always one of our worries, is when we see development occurring on these old landslides, which of course could be reactivated in the future. So I think we'll head up the trail, head up the Ghost Flats Trail and get a closer look at some features of this landslide. Okay, here we are, maybe a quarter mile up the Ghost Flats Trail. So we're well within that landslide complex that I pointed out before. And so in addition to the obvious hazards of landslides, of your home or whatever is built on top tumbling down the mountainside, there's a phenomenon that's called piping. Because these landslide deposits have so much of those fine-grained silts and clays in the deposit, they are susceptible to erosion and what we call piping. And so kind of the end result of piping are sinkholes. And so there's a couple of them up here that are just off trail. that basically to get one of these pipes and one of these sinkholes to form, you need the fine grained deposits, and then you need somewhere lower down the slope where percolating water can daylight. And so in these landslide complexes, you typically get very hummocky or uneven terrain, including really shallow little basins where water collects. And if there's some place lower on the slope where that water percolates from the bottom of that basin through the landslide material and finds its way and daylights out of this deposit, over time that groundwater starts to speed up, and it'll actually start picking up grains, and eventually you'll get subterranean conduits that are open, and then eventually so much material gets washed out that you've got basically an underground cave that propagates up to the surface, and then you have sinkholes at the surface. And so you can see why these can be a problem. They can be very unpredictable in where they may pop up. And so it's a hazard not only to humans, to our infrastructure, if you happen to be built in an area that's susceptible to piping, but to livestock as well, that could easily fall into these holes. So that's just kind of an interesting feature and an additional hazard of landslides that not many people are aware of, but is quite common in the landslides here above Cedar City. Okay, we'll move on. Whoa. If I fall, dude, you got to get it. Okay, here we are near the base of the main body of the Jurassic Navajo Sandstone. We have, from our last stop, we've come down the Ghost Flat Trail and have now joined back on the Thors Hideout Trail, and we're maybe a quarter mile at the most up from that junction on the Thors Hideout Trail, where it kind of jogs into one of these little side canyons and gives us a really up close look into the Navajo Sandstone. And so a common question when I hike with people through Thunderbird's Garden are about these pits that commonly develop in the Navajo Sandstone and other sandstone units. They're very common. Geologists call it pit weathering, or also taphony is another word that we'll commonly use. And normally these pit weathering holes start to form. It's got to start with some kind of imperfection in that sandstone. So oftentimes there'll be some sort of weakness, and in this case, because these rocks have been folded and kind of beat up over millions of years, there's lots of fractures, brecciation that are running through this rock, and those are often the nucleus for a taphony or a weathering pit. And so once you get that weakness and you get a little bit of a cavity formed, and then it's mostly chemical weathering. So it's basically rainwater that is always kind of slightly acidic that starts to attack the cement that's holding those sand grains together. And if you've got that little cavity already formed, that increases the surface area versus the rest of the rock. And so once you've got that increased surface area, that weathering action can work at an accelerated rate, and it starts to eat away in the rock, kind of in that spherical fashion into the rock, and you end up with those weathering pits. And so another interesting thing and common thing you see here are those dark streaks. That's what we call desert varnish. And that takes thousands of years typically to develop, and that's kind of a combination of oxidation of the iron-rich minerals that are in the rock, basically rust, and then also there are living organisms that are commonly part of those dark streaks that gives it that dark color. So there's kind of an organic component and then also that oxidation component to get those streaks that develop, those vertical dark streaks that develop on the rock. Okay, so we'll keep heading up the Thors Hideout Trail here to a really interesting overlook. Here we are at the top of the Thors Hideout Trail, and we're basically at a topographic divide or a pass between Thors Hideout Canyon to the north, and to the south is Red Hollow, and at the bottom of Red Hollow is Cedar Canyon and State Route 14. And so we'll probably end up ending the tour here. We've got a thunderstorm that's kind of bearing down on us. If you continue to the east, there is a short little spur from this pass that will take you up to Thors Lookout, which takes you a little bit higher. And I definitely recommend taking that trail up. And there's even a little rock bench at the top you can rest your legs at. So this is really kind of the crescendo, in my opinion, of the Thunderbird Garden area in terms of just really interesting scenery that you can see from this vantage point, as well as the interesting geology. And so first we'll look off to the north here, and it kind of puts into perspective a lot of the things we've been talking about, and I'll try and point out some of the rock formations. So our previous stops in the canyon, we were down in this low area in this canyon, is where the trail was on some of the previous stops. So on Skyline, these are those Cretaceous rocks, and here they're actually in place. These aren't part of a landslide. This is the Cretaceous rock mountain that's behind the Fiddler's Canyon subdivision. So just on the other side of these Cretaceous rocks, you drop down into Fiddler's Canyon. So these are in place. And then down here lower, this is the landslide. So this landslide material originated higher up in these in-place Cretaceous rocks and flowed down over the existing land surface, which were these tilted Jurassic rocks. And so of course we've got the Navajo Sandstone that we looked at up close and personal down by the trailhead. And then this gives us a pretty good vantage of what's above the Navajo Sandstone. So once you get above the Navajo Sandstone, you get into some different colored rocks here. And the first one you come across, there's kind of some red mud right at the top of the sandstone, and also some white alabaster gypsum. And that is part of the Temple Cap Formation, also Jurassic in age, which you can also see down in Zion National Park. And so above that little streak of red and white of the Temple Cap Formation, you get into the Carmel Formation, which is a series of limestones and mudstones and more of that white alabaster gypsum. And you'd be able to recognize that alabaster gypsum because of the mine that kind of down in Cedar Canyon near the Rusty's restaurant is an active gypsum mine where they're actively mining out the Paria River member of the Carmel Formation gypsum. And you can just see that little white spot at the end of my stick here is that Carmel alabaster gypsum. And so that's what's going on there. And so if we look to the south now, down Red Hollow, and you'll want to come over here so we can get a good look down the hollow and look at some of the structures that are on the, so this would be the opposite side of Cedar Canyon. And there's this is Lone Tree Mountain. Locally we just call it Cedar Mountain, but I think on the maps it's officially called Lone Tree Mountain. And this is one of the coolest structures. I had talked about the severe orogeny and that mountain building event. And one of the neatest structures that you can see in the Cedar City area is this thrust fault. So right here we have the orange Navajo Sandstone. And then there's a really distinct break right there, and that is a thrust fault, a compressional fault, where the Navajo Sandstone and adjacent units were compressed, faulted, and thrust up over Carmel rocks. So these Carmel rocks, as we were looking at on the other side of the canyon, these are normally on top of the Navajo Sandstone, but here we actually find the Navajo Sandstone on top of the Carmel, that gypsum and that limestone of the Carmel Formation in this thrust fault relationship. And so you can see it really well over there, and it's one of the coolest structures you can see and is a testament of this mountain building event that occurred about 80 to 65 million years ago. And so, of course, that mountain building event has nothing to do with the mountains we have here today. The Basin and Range Mountains, the Colorado Plateau, these are all due to the current tectonic regime, which is mostly extension. You know, rather than compression and thrust faults, we have extension, and we have extensional faults, which we call normal faults. And of course, the most famous of which is the Hurricane Fault, which is about 150 miles long, that extends from Cedar City down to the Grand Canyon. And that's what has created the mountains that we have here today. So here in the immediate area, here at the pass, again, we find ourselves in another one of these strike valleys. So we got a nice kind of V-shaped valley to our north, a V-shaped valley to the south. And again, the way we get these strike valleys are when you have resistant units that are kind of bounding this valley, and you've got softer units in the middle that are more easily erodible and wear down over time. And so here we're in the middle of the Navajo Sandstone, but kind of unique to Cedar City is we actually have two large ledges of Navajo Sandstone. If you go down to Zion National Park, there's just one big 2,000-foot pile of Navajo Sandstone. Here at Cedar City, we've got a lower layer of Navajo Sandstone, which makes up the Red Hill, the prominent Red Hill just east of town. And then above that, we've got the Kayenta Formation, which is the Cedar City tongue of the Kayenta Formation, which we're standing on right now. That's the weak intervening layer that erodes very easily and creates the floor of the valley. And then just to our east is the main body of the Navajo Sandstone. So this lower ledge we call the Schertz tongue of the Navajo Sandstone. We are on the Kayenta, which is weaker and more easily erodible. And so I can kind of point these out. So we're on the Kayenta at the bottom of the canyon. This is the Schertz tongue of the Navajo Sandstone. And if we pan up to the mountain, to the east side of this valley, all of the Navajo Sandstone up there is what we call the main body of the Navajo Sandstone, which holds up the east side of the valley. And so another typical example of a strike valley, which we have many of, and another name for at least the high points, we call them cuestas or hogsbacks. And that, of course, is a relic of the fact that all of these rocks have been folded and are up at about that 45-degree angle. And so you get those jagged, eroded edges of those more resistant sandstones that create that type of topography with all of the strike valleys. Okay, so I think those are the highlights that you can see from here. I hope you've enjoyed the tour of the Thunderbird Garden area. And I definitely recommend, we did it on foot. It's equal, a lot of these trails are equally as fun on a mountain bike. Some of them can be a little sketchy, but either way, the geology is a huge draw, and I definitely recommend coming out and exploring. Thank you.